Hey guys, ready to start chapter 9? Of course you are. Mixtures. Let's talk about mixtures a little bit. We've learned about mixtures before, right? We learned about homogeneous mixtures versus heterogeneous mixtures. If you remember, homogeneous mixtures are mixtures that are the same throughout. So if I thoroughly mix salt and water and I take a sample somewhere in that salt water mixture, I'm always going to get salt water. But heterogeneous mixtures where you can take a sample and you're not going to get exactly the same throughout. So for example, I'm eating my Crunch Berry cereal. I take a bite in one spot and I get nothing but Captain Crunch. I take another bite in a different area and I get nothing but the berries, which wouldn't be such a bad thing. And but it's varied, right, depending on where you take your sample. So that's a heterogeneous mixture. Homogeneous mixture is what we're kind of focusing on today. So we want to talk about mixtures in general. Want to define some terms for you. I know what you're thinking. You're like, Mr. Walker, I've been doing mixtures most of my life, right? As a little kid, I would mix dirt and water together and make mud pies. I don't know if kids actually do that anymore, but I did that when I was a little kid. So, we've been mixing things for a long time, right? So you think you've got it figured out, but do you?
Do you?
Well, we'll see. For example, can you tell me why it is that salt will dissolve in water, but if I try to dissolve oil in water, it won't work? How about why is it that if I add sugar to my tea to make it sweet, at some point, no more sugar will dissolve? Answer me that question. Here's something pretty cool. Did you know that you can mix some liquids together and all of a sudden a solid appears? It's like magic, right? And then what we want to talk about last of all today is concentration, right? The concentration of substances inside a mixture, and we'll do, of course, some math surrounding that, some calculations because you guys enjoy that so much. All right. So all of this and more today on Chemistry with Mr. Walker. Okay, so let's talk about these homogeneous mixtures, and let's define a few terms to start with. First of all, let's define the term solution. What is a solution? A solution is a homogeneous mixture. Remember, that's a mixture that is the same throughout. You take a sample here or some other place, it's going to be the same. The content's going to be the same of that sample. So a solution is a homogeneous mixture of two or more substances. All right, that's a simple definition of a solution. So it could be, we often think about a solid mixed into a liquid, like we've talked about dissolving salt in water, but it can also be a gas mixed with a liquid. Every time you pop open that soft drink can and you hear psh, it's because carbon dioxide has been dissolved in that liquid, right? It could even be a mixture that has nothing to do with liquids. You could have two solids that are mixed together. For example, if you mix copper and zinc, you get brass. And by the way, we typically refer to that as an alloy, a metal that's mixed with some other solid. A lot of different types of mixtures that we can refer to as solutions. But now let's define, in all of these, what do they have in common? Well, you have something that you're dissolving into some other substance, right? And so let's define what is the thing that is dissolved versus the thing that it's dissolved into, all right? So we've basically got two terms that we want to consider for that. First of all, you have the term solute. A solute is the substance or the substances that are dissolved into a solution, okay? So the things dissolved, that's what we refer to as the solute. The solvent, on the other hand, the solvent is the thing that the solutes are dissolved into, all right, into which the solutes are dissolved. So we need to understand those two terms so we can dig deeper into our discussion about solutions. So why is it that solutes dissolve into solvents? And why is it that some substances we can't get it to dissolve in other substances? I mentioned earlier, vegetable oil will not dissolve in water. So why is that? Thankfully, God's not limited as we are with such things that normally don't mix. Galatians 4:4 and 5 is a tremendous example of that. Listen to what that says. But when the fullness of time had come, God sent forth his son, listen to this, born of a woman. What? Born of a woman? He's God, right? How can God be mixed with man? Born of a woman. Listen to the rest of it. Born under the law. How could God be under the law when God invented the law, right? Why did it have to be this way? Why did this mixture have to be made? To redeem those who were under the law, that we might receive the adoption as sons. How can Jesus Christ be the God-man? Well, only God can do that. And thank God that he did, because now there's a sacrifice for the sins of those that trust in him. But what about the mixtures that God has defined in the laws that he has created in nature? Why do some things dissolve in other things? And so let's talk about that for a moment. And let's begin with considering ionic substances. A substance that is considered to be ionic, an ionic compound, is a compound that's held together by opposing electrical charges, right? Salt's a great example of that. It's a simple example of that. We talked about dissolving salt in water. Why does that work? Well, salt is comprised of a sodium ion combined together with a chloride ion, right? The sodium atom gives up an electron and becomes positively charged, and it gives that electron to a chlorine atom, and so the chlorine atom becomes negatively charged. And so these opposing charges are what hold the sodium and the chlorine together, right? So you've got these charges inside of ionic compounds. Well, we also learned something a couple of chapters back about water, and that is water carries partial charges, right? Because water is what we refer to as a polar covalent compound, right? The way that the water molecule is held together is by a physical bond, a covalent bond. But because and they actually share electrons, right? But because the electrons are not shared equally, the hydrogen atoms in the water molecule have a partial positive charge, whereas the oxygen atom in the water molecule has a partial negative charge. Okay, and it's because water has these partial charges that it will that you can dissolve salt into water. All right, so there's actually a diagram, a picture that I want you to see in the book that just gives you a pictorial example of why this works, and that's on page 258. And so you notice in the left part of the image there, you have what we refer to as this crystal lattice structure. It's these sodium and chlorine atoms that are bound together by these electrical charges, right? And so when you put the salt into water, we see what happens in the right side of that picture. Notice how the water molecules, they begin to pull apart the sodium and the chloride ions, and the water will rotate and surround either the sodium ion or the chloride ion, depending on what charge the particle is that it surrounds. If it's going to surround the sodium ion, which is positively charged, then the water molecule will rotate so that the oxygen atom is the part that's around it, right? Because the oxygen carries a partial negative charge. And likewise for the chloride ion, the water will rotate itself and orient itself so that the hydrogen atoms in the water molecule, which carry this partial positive charge, are surrounding the negatively charged chloride ion, right? So this is an important point, right? When ionic compounds dissolve, they split up into their individual ions, okay? They split up into individual ions. Why am I making that point? Well, the next substance I want to talk about is polar covalent compounds being dissolved in other polar covalent compounds. Why does that work? Well, again, it works because polar covalent compounds carry a partial charge, right? Partial positive and a partial negative charge. And for that reason, you can dissolve polar covalent compounds in other polar covalent compounds. Now, we've got another picture that we can look at to help understand the way that works, and that picture is on page 259. And so if we take a look at that, you see here that the water molecules, again, you've got a polar covalent substance that's dissolved in water, and again, the water molecules orient themselves so that the opposing charges in the water molecule will surround those opposing charges in the other substance. And so that's why you can dissolve polar covalent compounds in other polar covalent compounds. But here's the difference between polar covalent compounds being dissolved in polar covalent compounds and ionic compounds being dissolved in polar covalent compounds. where we said that the ionic compounds split apart when they're dissolved into separate ions, polar covalent compounds separate into their individual molecules whenever they're dissolved in another polar covalent compound. And why does that matter? Well, because of that usually when you dissolve an ionic compound in a polar covalent compound, you form a solution that will conduct electricity, right? Because it splits into separate ions. Those ions can move freely in there. And if you remember, what is electricity? Electricity is the flow of electrons. It is the flow of negative charges. And so these negatively charged particles are able to flow freely because they've been separated from one another. We can't have that when we dissolve polar covalent compounds because they don't actually split apart into separate charges, right? The molecules still stay intact. It just separates into individual molecules, and that's why it dissolves in the solution. Okay, so now that we understand why some substances will dissolve in other substances, let's define a few other terms. The first term we want to define is solubility. Solubility tells us how much solute can be dissolved in a specific amount of solvent. And it's usually given to us in grams of solute per 100 grams of solvent. Okay? So we've established the fact that certain substances cannot dissolve into other substances. For example, you can't dissolve oil in water. We've talked about that. You can't dissolve an ionic compound in a purely covalent compound. Why? Because there aren't any partial charges in purely covalent compounds. And you got to have partial charges in order for that ionic compound to be split apart into separate ions and actually dissolve, right? So that's important to understand that, but we also need to understand when we talk about solubility, we need to understand how much of one substance can we dissolve? How much of a solute can I dissolve in a certain amount of solvent? In the example of salt into water, the solubility of salt into water is 35.9 grams of salt per 100 grams of water. And so what that means is if I have 100 grams of water and then 35.9 grams of salt, I can dissolve every bit of that into that water, but if I try to add 1 more gram of salt, it's not going to dissolve. The solubility of salt into water won't allow it. Now, there are a few things that will affect that. What if I wanted to get just a little more in there? Can I? Maybe. And one of the things that will affect that is, as you may have guessed, temperature. So there's a couple of things to remember regarding temperature and how it affects solubility. The solubility of gaseous solutes decrease with increasing temperature. So we need to know that rule. Also, the solubility of most solids increase with increasing temperature. Now that'll sort of make sense to us if we think about a couple of things. This is the way that I like to remember it. Hot Coke goes flat quicker, right? The solubility of gases decrease as temperature goes up. So if I want to keep my drink kind of fizzy, my soft drink fizzy, I should stick it in the refrigerator instead of leaving it on the counter. On the other hand, when it comes to solids, if I have cold iced tea and I try to dissolve sugar in it, that's not going to work very well. I can increase the solubility of my liquid, of my tea, by heating it up, right? And then I can begin to dissolve the sugar. So increasing temperature will increase the solubility of solids, whereas increasing the temperature will decrease the solubility of gases. Okay, so that's one thing that's important to remember. That's not the only thing, though, that affects solubility. The solubility of gaseous solutes increases with increasing pressure. Pressure also affects solubility, right? So whereas increasing temperature causes gases to be less soluble, if you increase the pressure, they're actually more soluble. And again, a can of Coke is the best way, in my opinion, to remember that, because as long as that can is sealed and those contents are under pressure, that carbon dioxide will stay dissolved in that liquid. But as soon as I pop the top on that can, right, carbon dioxide is beginning to be released from that solution, and you're going to lose fizz over time, right? So keeping it under pressure, the higher the pressure, the more soluble those gases are. All right. There's one other thing that we need to talk about, and that is what we refer to as a saturated solution. What is a saturated solution? A saturated solution is a solution with the max amount of solute in it. I can't fit any more in that solution, right? The solubility of that substance in this solvent at this particular temperature and under this pressure, that's as much as it will allow. And so we refer to that as a saturated solution. It won't hold anymore. So make sure you understand those definitions, and then we can talk about some of the other properties of solutions.